We're going to take a look at bipolar junction transistors as common emitter switches. The bipolar junction transistor, or BJT, is one of the most common types of transistors, and it works as a current amplifier. A small current can be used to control a large current. The transistor can function as a switch or an amplifier. We're going to show you how to use the BJT as a switch in a common emitter configuration. The bipolar junction transistor has three terminals, and they're named base, collector, and emitter. The base terminal is basically the control signal input for the transistor. The collector is the output of the transistor. This is where we're going to control a large current. And the emitter is a common terminal that functions as a current return path for both the control signal and the larger current that we're trying to control. Let's wire up this NPN BJT as a common emitter switch. Before we do that, let me explain a little bit about the two main types of BJTs. There's the NPN, or negative positive negative type, and there's the PNP, or positive negative positive type. The first one we're going to look at is NPN. And you can tell them apart because of a small arrow on the transistor diagram between the base and the emitter. This arrow represents an internal diode, and current is only allowed to flow in one direction. In the case of an NPN transistor, current can only flow from the base to the emitter. That's why the arrow is pointing towards the emitter. In a PNP transistor, the arrow is also between the base and the emitter, but it's pointing the other direction, toward the base. We're going to create a small circuit that allows current to flow into the base and out of the emitter. A current flow through the base emitter junction is what turns on a bipolar junction transistor. And to turn it on, we need to put a positive current into the base, and then we need to take that current back out of the emitter and return it to the power supply. I have here on the left a 5-volt power supply, and we're going to wire it up to this transistor. I'm going to use a switch so we can turn the control signal off and on. And I'm going to allow the current to return from the emitter. Got some small wires here. And I've got some components already picked out. I've chosen these components based on the voltage of my power supply, the requirements of the transistor, and the current that we're ultimately going to control, which is a LED current. And here's the LED. This is an LED that has a 2.1 volt forward drop. That means when current flows through it, the voltage drops by 2.1 volts through the LED junction. And I've sized some resistors appropriately. Now this represents a small signal NPN transistor. It only takes about 5 milliamps to turn it on pretty solid. So if you do a calculation, take 5 volts, subtract the base emitter drop, which is probably about 0.7 volts. And according to Ohm's law, to get 5 milliamps of current through this junction, we are going to need a resistor that's right around 1 kilo ohm, or a little bit less. So I've picked a 1K resistor, and we're going to put that in right here. Let's start the simulator and see what happens. Clock is running, but no current is flowing yet because my switch is open and we don't have a complete circuit. If I close the switch, current's going to flow from the positive terminal of the supply through the switch, through this resistor, and remember the purpose of this resistor is to limit the current to the base. We only need about 5 milliamps of current to turn the transistor on. If we put too much current into the base, we could destroy the transistor. And then of course the current flows into the base, out of the emitter, turning the transistor on, and then through these wires back to the negative terminal of the power supply. Let's close the switch. As you can see, a small amount of current is flowing, represented by the small yellow dots that are moving, and the current flow is indicated by the direction of the movement. As you can see, current is flowing through our switch, through the current limiting resistor, into the base of the transistor and out of the emitter, back to the supply. At this time, the transistor is turned on, but it's not really doing anything because there's nothing connected to the collector, which is our output terminal. This is where we need to connect our our large current that we're trying to turn off and on. So let's wire that up instead. Let's open the switch and connect our LED. Now the LED is pointing down, which means current is going to flow in a downward direction. And when a bipolar junction transistor is on, current is allowed to flow between the collector and the emitter. In this case, we want the current to flow into the collector and out of the emitter. Because of the direction of this arrow on the emitter, that's the only way that it will really work in a common emitter configuration. So here's our diode, and we're going to have to connect it to the positive supply. It's already connected to the negative supply when the transistor is turned on. Imagine a jumper between the collector and emitter. Essentially, when the transistor is turned on, the collector and emitter will be shorted together. But we do need a positive supply on this end of the LED. And I've picked out another resistor, which is a 160 ohm resistor, which is sized to give us about 20 milliamps of current through the LED. Most small LEDs are designed to run at a maximum of 20 milliamps of current. Too much current, they'll burn out. We're going to connect the positive terminal to the positive of our supply. Here we go. Now, as you can see by the green color, there is a positive voltage available to the LED. But where does that positive voltage stop? In the transistor. The transistor is off right now. No current is allowed to flow into the collector and out of the emitter until we turn the transistor on. There again, we do that by simply applying a small amount of current to the base by closing the switch. And now you can see the circuit in action. A small amount of current is flowing into the base, turning the transistor on. Because the transistor is on, a large amount of current is allowed to flow into the collector and out of the emitter. It's a 3-terminal device and it makes a very effective switch. We can open this switch and the LED will turn off. Close the switch, LED turns back on. The movement, the speed of the dots, the yellow dots, indicates the amount of current that's flowing. And as you can see, there's more current flowing through the LED than there is into the base of the transistor. We are effectively controlling a large current flow with a much smaller current flow. And this transistor could probably control something more beefy than an LED, perhaps up to maybe a quarter of an amp. Right now through the LED, we have, if you look down here, about 19.52 milliamps of current. That's just under 20 milliamps. And through the base of the transistor, we have just a little bit less than 4.34 milliamps. Let's take a look at a PNP type transistor and how it's used as a common emitter switch. You'll notice in this circuit, using an NPN transistor, the emitter is connected to ground or to the negative terminal of your supply. And it's common. It's the common current return path for the switch control signal and also for the LED voltage. Both currents flow into the transistor and they flow out together through the emitter. So the emitter is common, and that's why this is called a common emitter configuration. What we're going to do is remove this transistor and put in a PNP type transistor. Now in a PNP transistor, things are really different. We have the arrow pointing in the other direction, and in this diagram, the emitter is on the top. Now they can be drawn either way, but it's more convenient for the emitter to be labeled on the top because of the way that these switches are used in a common emitter configuration. Now the situation here is very similar but different. Let me rearrange things so you can understand. Something different is happening this time. Let's take a look at what it is. Let's open our switch, or maybe leave it closed for now. What's happening is positive current from our power supply is flowing into the emitter. That's because the arrow is pointing towards the base. Just like an NPN transistor, current flow through the base emitter junction is what turns the transistor on. But in the case of a PNP transistor, current flows in the opposite direction. It flows into the emitter and out of the base, rather than into the base and out of the emitter, as it would be in an NPN transistor. So current is flowing into the emitter and out of the base through our current limiting resistor. This limits the base current to approximately 5 milliamps, and then through our closed switch back to the negative terminal of the supply. If we open this switch, we will break this circuit and no current will flow through the base emitter junction. You can see that there's a positive voltage available to the emitter and in the base and all the way through this transistor, but because our switch is open, there's no actual current flow. We have a positive voltage but no current. We close the switch, this circuit is complete and current is able to flow from the positive terminal into the emitter, out of the base, through the current limiting resistor, and through our closed switch back to the supply. Now with the current flowing into the emitter and out of the base, the transistor is on. And it's going to allow a larger current to flow into the emitter and out of the collector. So here, once again, the collector is our output terminal, but we have a larger current flow. It's also approximately 20 milliamps, just as it was in the last circuit. Here we have our current limiting resistor for the LED, and you can see current is flowing from the positive terminal of the power supply into the emitter, out of the collector, through our LED current limiting resistor, through the LED, and back to the negative terminal of the supply. So this is how a PNP transistor is used in a common emitter configuration. And even though the emitter is not grounded or connected to the negative terminal of our supply, it's still a common terminal. You see, this is the common terminal for the current flowing into the transistor. The current that flows out of the base and the current that flows out of the collector, both currents flow in through the emitter. So it's a common emitter configuration, but in this case for the positive current flow to come in instead of the negative current flow coming out or on the NPN transistor. How can we use transistors to invert a signal? What that means is in a logic circuit, a positive voltage is usually considered a logic high or a logic 1. It's a signal that represents perhaps turning something on, whereas negative voltage or 0 volts represents a logical 0 or what's called logic low, which may represent turning something off. And we're going to see how a transistor can easily convert a logic high signal into a logic low signal or vice versa. Let's disconnect these transistors. And let's go back to our NPN configuration. Okay. We're going to put the LED aside for the moment. So here's our little circuit. Something is not quite right here. I'm getting an error. Infinite matrix. Don't really see anything wrong, but could have something to do with this other transistor being out here. Okay. When we close the switch, small current flows through our base, out of the emitter, just like we saw the first time. And the positive voltage coming into the base could be considered a logic high signal. What I'm going to do is put a scope probe so we can see the voltage right here. Okay. As you can see, with the switch closed, we have a high level signal here. It's a 5-volt signal. When we open the switch, that drops to a low level signal. So this is a logic signal, It can be in two states, either high or low, and that's controlled by the switch. High signal, low signal. We're going to use this transistor to invert the signal. What we're going to do is use another 1K resistor and we're going to connect that to our power supply. And let's put another scope probe on that. Go ahead and stack these so we can see them next to each other. Now what do we have right here? We have two different signals on our scope. One is the input signal and one is the output signal. The input signal is technically logic low. It looks like the line is up, but if you look at the scale here, it's less than 0.1 volts, 98 millivolts. So that's just a small amount of leakage current that's coming through the transistor. It's nothing to worry about. We could definitely consider this input here to be a logic low. If you want to, you could use a small bleed resistor to dissipate that leakage current. It's going to look a little ugly, but let's just put it right here. Let's use a 10K resistor. And we can wire that to the ground. Okay. Actually, let's make this prettier here. So our scope probe, our 10K resistor to ground. Now with our switch open, we have a very, very low voltage on our input. 500 picovolts. Nothing to worry about. On the output though, we have a 5-volt signal. Where's that coming from? The transistor's off. Well, that's coming from this 1K resistor, which is tied to the 5-volt positive terminal of the power supply. So with the transistor off, we automatically have a 5-volt output signal. When we turn the transistor on by closing the switch, small amount of current flows into the base, and that turns the transistor on. Because the transistor is on, the collector is tied to the emitter internally. They're connected together, and therefore the collector is basically connected to the ground or the negative terminal supply, which is what the emitter is connected to. So the voltage now on the output is approximately 0 volts. Okay, very, very low, 11 millivolts. So if we open and close the switch a few times, you can see down on the scope that it is an inverter. A logic low level signal becomes a logic high, and a logic high becomes a logic low. Let's use another transistor to invert this signal again. We'll leave this scope probe right here, that one right there. Let's add another transistor. Let's tie the emitter to ground. Let's put a current limiting resistor in here. Nice thing about using a simulator is you can't really blow anything up. We're going to use a smaller value resistor here. this needs to be a larger value. And let's add another scope probe. Okay. Now we have all three signals. We've got a logic low in. In the middle of the circuit, we have a logic high, nearly 5 volts. In a 5 volt CMOS logic circuit, anything above 2.5 volts is considered high. Anything below 2.5 is considered low. And on our output, we have a logic low, 13 millivolts. If we close this switch, you'll see everything gets inverted. Logic high coming in, logic low in the middle, logic high coming out. We can open and close the switch a few times, and you can clearly see we have an inverter connected to another inverter. Let's take a look at the analysis of this circuit. When current is flowing into the first transistor, it's turned on. And so its collector is connected to the emitter, and the emitter is connected to ground. So essentially the collector is connected to ground, and the voltage on the collector will be 0 volts. Current will flow through this limiting resistor, about 20 milliamps in this case, but the voltage here will be 0. And that's an inverted signal, by the way. Switch is on, 5 volt signal here, 0 volt signal here because the collector is connected to the emitter. When this switch is open, positive voltage through this 220 ohm resistor and then through this 1K resistor feeds the base of this transistor, turning it on. Because it's on, its collector is tied to the emitter, which is tied to ground, so the collector is at 0 volts and the voltage here is 0. When that transistor is off, this 1 kilo ohm resistor pulls the collector high and you have a 5 volt signal. So we've got a lot of resistors going on here, and I know it can be a little confusing, and there's different names that we use for them. This first 10K resistor is just a bleed resistor. It's designed to dissipate a very small amount of leakage current out of the base of the transistor. It's probably not necessary in a lot of circuits. In fact, we can remove it from this circuit right now, and you're really not going to notice any difference. You'll see here our scope down below looks pretty much the same. So we'll ignore that one. The first resistor is a current limiting resistor for the base current. That's to prevent us from blowing up this transistor. We only need about 5 milliamps of current into the base to turn it on. This other 1K resistor also performs the same function. It limits the current to the base of this transistor. These other two resistors, their purpose is to pull the collector to a high voltage when the transistor is turned off. See, the transistor really only does one thing. When it's on, it connects the collector to the emitter, and it's like a short or a jumper. Well, that connects the collector to ground, but what about when the transistor is off? What does it do then? By itself, the transistor does nothing. If there's nothing else connected to the collector, there's not going to be any positive voltage there because there's no place for it to come from. That's what these other resistors are for. These are called pull-up resistors, and they pull up the collector to the positive voltage when the transistor is not being turned on. When the transistor is on, the transistor has a very high conductivity from collector to emitter, and essentially the collector voltage is pulled back down to ground. And there's a voltage differential across this resistor. Why did I use a 220 ohm resistor here and a 1 kilo ohm resistor here? Well, I did that so that we will have a high voltage at this point. Let's put a 1K resistor there to demonstrate. Circuit will still work with a 1K resistor. This transistor is still on, which means we have a logic low output, a logic low input. But our middle voltage right here is a little bit lower than 5 volts. In fact, it's going to be closer to 2.5, maybe a little bit over 3. Let's wait here till the scope scrolls off and see what that peak is. Yeah. 2.82 volts. Why is that? Well, it's not important if you don't need to use the signal in the middle of the circuit. If we're not going to use a scope probe or connect anything else here, this circuit is perfectly adequate and very reasonable. But what's happening is, why is the voltage only 2.8 volts here? It's because these two resistors are essentially connected in series. Current flows in through this resistor, and then through this resistor, and then into the transistor, out the emitter, back to ground. Whenever you have two resistors in series, the voltage in the midpoint is going to be somewhere between this voltage and this voltage. So up here we have, let's look at this wire, we have 5 volts, and then down here we have 0 volts. And at the base it's a little bit higher actually. It's 631 millivolts, just over half a volt. And that's because there's a voltage drop from the base of the emitter. If the emitter is 0 volts, the base here is going to be about 0.7 volts higher. But so basically between 5 volts and 0.6, we are ending up with an intermediate voltage in the midpoint between the two resistors. And this is called a voltage divider. You can look it up online. I'll make a video about it in the future. And because these two resistors are the same value, we're going to get exactly half. The voltage is going to be an exact average of 5 volts and 0.631 volts. So, as you can see, 2.82 volts it is. Not a problem because it doesn't take voltage to turn on a transistor, it just takes current. And through this resistor right now we have 2 milliamps, and that's enough to turn it on. But if you do want to kind of get closer to 5 volts, you'll just need a stronger pull-up resistor here. And that's going to bring this voltage up to 4.21 volts. If you find a voltage divider formula, you can see, if you plug in the 220 and the 1K, you're going to get a voltage very close to that. So there you have two inverters in a row. Had some questions on YouTube about how that works, and here's the answer.